So let us start with the definition. So any extension field of degree 2 over this field of rationals is called a quadratic field. So the first proposition we want to prove in this lecture is this: every quadratic field is of the form root of d adjoint to rationals where d is a square free integer. So let us see the proof of this. So say k is a quadratic field, then you take an element x in k minus the rationals. So that is, k is just a quadratic field, and then you have just taken rationals out of it. So this is of degree 2 over rationals, because we are saying the quadratic field has degree 2 over rationals. So therefore this x is a primitive element of k, precisely because you can write k as this rationals adjoined with x. So you're just taking x out of k minus q, and this 1 comma x is a base of k over q, because the degree is 2. So there are two elements here. So let this be a polynomial here. F of x is x square plus bx plus c, where b and c are rational. So you can see it's a monic polynomial. It's 1 times x square here. So say this is the minimal polynomial of this element x which we have picked from here. So now we can solve this equation. This is a quadratic equation: x square plus bx plus c equals to 0. And we can solve this to get 2x is equal to minus b plus minus square root of b square minus 4ac. So everything is just adjoining this to rationals, because only this thing can be irrational. Everything else is just rational numbers. So the field would be q adjoined with square root of b square minus 4c. So by b square minus 4c we mean one of the two elements. It could be, the square root could be positive or negative. So one of the two elements of k whose square is b square minus 4c. So it could be positive or negative. So now b square minus 4c by itself is a rational number, precisely because b and c are rationals. So b square minus 4c is a rational. Since it's a rational number, you can write it in the form u by v. So this we will again rewrite it as uv divided by v square, precisely because there is a square here and we can take this out of the square root. So with uv as integers. So then you can see that k is just rationals adjoined with square root of uv, because it is b square minus 4c square root, and we are saying b square minus 4c is u by v, which is uv by v square. So this v would come out and get absorbed in the rationals. The only thing we are left with is square root of uv, where u and v are integers. So essentially we are saying that now it is possible to write k as rationals adjoined with some root d, where d is a square free integer and d is plus or minus a product of distinct primes. So if d is positive, this root of d adjoined to rationals is called a real quadratic field. If d is negative, then this root of d adjoined to rationals is called an imaginary quadratic field. So basically nothing much has been done in this. We have to solve such an equation, and then we come to b square minus 4c, and then we just say that, you know, this at its worst could be a integer like this d, which could be positive or negative, and just coming from this solution, nothing else. And basically because b square minus 4c is a rational number, which we can write like this. So now we come to the theorem which we want to prove for this lecture. So let k be this quadratic field. So you have taken root t and adjoined to rationals. So basically we are taking this from the proposition. So this is a quadratic field with d a square free integer. So it is square free. That means precisely it cannot have 2 square or 4 in it. So it cannot be 0 modulo 4. So it does not have a factor of 4, precisely because it is square free. So if it is not 0 modulo 4, it has to be either 2 or 3 modulo 4, or it is 1 modulo 4. If it is 2 or 3 modulo 4, then this ring OK of integers of k, this consists of elements of the form a plus b root d, where a and b are integers. So we can compute the ring of integers of this field, and that will be of the form a plus b root d, where a and b are integers. If d is 1 modulo 4, then this, our ring of integers, will consist of elements of the form 1 by 2 u plus v root d, where u and v are of the same parity. So both of them are either even or both of them are odd, but at the same time. So if both of them are even, then you can divide by 2 and this again becomes of this form. But if both of them are odd, then you have u divided by 2 and v divided by 2. So let us prove this. So the element square root of d, this is root of the irreducible polynomial x square minus d. So this element root d has a conjugate in k, which is this root d adjoint to rationals, and this conjugate has to be minus root of d. So that is just roots of this polynomial when you set it equal to 0. So these are just the two conjugates. So you have an automorphism, just like in Galois theory, which will send the square root of d to minus square root of d. So any element of k is of the form a plus b root d, where a and b are rationals. So that is because k is just rationals and you have a joint square root of d to it. So this a and b are rationals. So now you apply sigma to it. This a plus b root d will get mapped to a minus b root d. So now let us consider this ring of integers of k. So that is the elements x in k which are integral over integers. So say you take x in our ring of integers. So if x is a root, then sigma x is also the root of the same equation, because the elements of this OK are integral over this ring. So you will have a polynomial whose root will be this number, but then sigma x will also be the root of the same equation for integral dependence, where sigma is just this sends x to its conjugate. So this will be the root of the same equation of integral dependence, same as x. So sigma x would also lie in our ring of integers of this field k. So then we have x plus sigma x would lie in O of k, because this is ring of integers. So it will have the sum of and product of two elements. So sum lies in here and product lies in here. But as we know, the elements of ring of integers, they are elements of k. We are choosing them, those elements of k which are integral over z. So these are of this form a plus b root d, precisely because elements of k also look like this, and this lies within k. So this is x is equal to a plus b root d, and x plus sigma x. So you can see that sigma is this. So you add this with this, you just get 2a, and then you multiply this with this, you get a square minus db square. So to start with, a and b are rationals. So this is rational and this is rational, and d is just a square free integer. So a and b are rationals, d is a square free integer. So this is rational and this is rational. But this integers is a principal ideal ring. Now since this is a principal ideal ring, it's a principal ideal domain actually. You can make it even more restrictive because there are no zero divisors here. So therefore it is integrally closed. So it's a PID and therefore it is a UFD, and UFDs are integrally closed. So this is integrally closed. So therefore these elements which are integral, because both these elements lie in the ring of integers here. So both these elements plus and this product lie in the ring of integers, and they are integral over z. So, and this is integrally closed, so there is no option but for them to be integers. So they are integers precisely because z is integrally closed. So PID lies within UFD and UFD is integrally closed. So let us recall again what we have done. We said since z is principal ideal ring and therefore it is integrally closed, we see that 2a is an integer and a square minus db square is an integer. So above, both these conditions are necessary and sufficient for this x, which is a plus b root d, to be integral over z, precisely because now this x is the root of this equation, x square minus 2ax plus a square minus db square equals to 0, because sum of the roots is 2a and product of the roots is a square minus db square. This is product of the roots, this is the sum of the roots. So that is fine, because this was x plus conjugate of x, this was x times conjugate of x. So this was x times this, and this was x plus sigma x. So now our job is actually, we know that 2a is an integer, we want to show that 2b is also an integer. So from the equation above, we have a square minus db square. If we multiply with 2 here and 2 here, this will still lie an integer, because if this is an integer, multiplication by 2 is not going to break anything. So you say 2a square minus db square will also be in integers. Now from here you already know that 2a is an integer. So if 2a is an integer, this entire thing is an integer, so this d times 2b square is also an integer. Now we are already given that d is square free. So if 2b we want to prove is an integer, so now we have to prove by contradiction. So if 2b were not an integer, so say 2b is not an integer, then its denominator would have to include a prime factor p. So if it is not an integer, it's a fraction of some form. If it is a fraction of some form, it has a denominator, and denominator will have a factor p. And this prime factor would have to appear as p square in the denominator of 2b square. So because we are talking about d times 2b square, so you have a denominator, you are squaring it. And then multiplication by d would not send 2b square into integers, because d is square free. You will have some p square in the denominator, and therefore d multiplied by that will not clear the fractions of denominator, precisely because d is square free. So therefore we have to conclude that 2b is in integers, because you will have a contradiction that d times 2b square lies in integers if we assume that 2b is not an integer. So we have to conclude that 2b is an integer. So therefore now 2a is an integer and 2b is an integer. So you can take a as u by 2 and b as v by 2 for some u and v as integers. So u becomes 2a and then v becomes 2b. So you can talk about now u square minus dv square, just like an analogy with this. But now you have this 2a and 2b, so this will lie in 4z, because you're squaring this, you will get 4a, you're squaring this, you're getting 4b. Precisely again because 2b is an integer, basically it has to be either odd or even. So you get u square minus dv square element of 4z just from this condition here. So this is useful. So if v is even, so if you see v is even, so we obviously this equation says this is equal to 0 modulo 4. So if v is even, so then you modulo 4 this portion out, this will also be 0 modulo 4. So this would imply that if v is even, u square is 0 modulo 4, because this term becomes 0 modulo 4. So then becomes u is even. So in this case a and b are integers. So now we have shown that this v is even, u is even, and in that case this a and b are just integers, because you can divide u by 2, get an integer, divide v by 2, get an integer, because u and v are even. So you get a and b as integers. In fact, this is true for both a and b. If d is 2 or 3, a and b are integers, and d is 1, but now we are saying u and v are of the same parity, that means both of them are even, and then you can divide by 2, you will again get integers here. So only thing left to consider is that if u and v are odd, then we get something like this, you have to divide by 2. So say this v is odd, so then v square is equal to 1 modulo 4. So this you can say 2k plus 1 square modulo 4 will just give you 1. So the possibilities modulo 4 for u square are 0 and 1. Again, because u is either even or odd. If it is even, if it is of this form, say some 2m square, if you take modulo 4 of this, it will be 0, or it is of odd square, then it will be 1. So the only possibilities for u square are 0 and 1. So only squares modulo 4. Now d is square free, so therefore it is not a multiple of 4, because anyway we are saying that d is anyway not equal to 0 modulo 4. It is not a multiple of 4. So since d is not a multiple of 4 and v square is equal to 1 modulo 4, so this equation is anyway u square minus dv square. This is equal to 0 modulo 4. That is what this means. Now we are saying that u square is equivalent to dv square modulo 4. But this v square is 1 modulo 4. So this becomes d times 1 modulo 4. So we have no option but for u square also to be 1 modulo 4, because otherwise u square would be 0 modulo 4 and d is non-zero. So we have no option but for u square to be 1, because u square has only two options, 0 or 1. 0 cannot fit in, 1 will fit in. So if you force 1 here, you have no option but d is equivalent to 1 modulo 4. So d is equivalent to 1 modulo 4, and that's precisely what we are saying here. D is equal to 1 modulo 4, where u and v are now both odd. So now in case d is equivalent to 2 or 3 modulo 4, so we are in case A. So we have something like this, a plus b root t, where a and b are integers. So our base is 1 comma root t. So this is base of our ring of integers over k as a z module. Now if we are in case B, t is equivalent to 1 modulo 4, then 1 plus root t by 2 and 1. So u times 1, and you can say 1 plus root t by 2. These are the this is the base. This is a z module base for ring of integers. So obviously 1 and 1 plus square root of d by 2 belongs to this O of k, because you can just put 1 and 1 here for u and v, or you can put u as 1 and v as 0. You get 1 and 1 plus root t by 2. Now we can also show that every such thing can be written as a linear combination of these two numbers, 1 and 1 plus root t by 2, with u and v of the same parity. So if they are both odd and we are given something like this, since we have to show that this is a linear combination of 1 and 1 plus root t by 2, first thing you can do is you can subtract 1 plus root t by 2 from it, because after all you're showing it's a linear combination of something like this. So you can subtract one of this and not destroy the structure. So you can subtract this if both of them are odd, because both of them have the same parity. So if both of them are odd, we can subtract from this, we can subtract 1 plus 1 times root t by 2. So then both of them will become even. So one can subtract this and reduce the problem to the case where u and v are both even. So then you can say the first part is u by 2 minus v by, you can rewrite this as u by 2 minus v by 2 times 1. So this one is our first basis, and then you can write v times 1 plus root t by 2. So this is the second basis. So we have been able to resolve any such thing if they are even like this, and if they are odd, you have to first subtract 1 plus root t by 2, and that doesn't matter because then it also expresses itself in the linear combination. So everything here you can find in the book. This algebraic theory of numbers by Pierre Samuel. So algebraic theory of numbers by Samuel. So this is a very good book.